All right, this is a Valentine's Day special, right? Today's Valentine's Day, so I decided that I was going to show one of the most, one of my favorite physics equation derivation ever, because, if there's anything that's true about people these days is that they love a person who's good at math, okay? And so I'm teaching you a little tip, okay, to be good at math and to, maybe get a Valentine, right? Okay, now if my camera will focus, I'll show you how this is going to work, okay? Okay, I'm going to show you this derivation, which is a derivation to get something that we call the range equation. But in the course of getting the range equation, I'm actually going to show you how we can get multiple other kinematic equations that are maybe not important for the scope of like high school physics course, and maybe for something more like college level physics, like university level physics, or maybe like engineering, like mechanical engineering. Okay. Okay. So here's what I'm going to do. Okay. I am going to first derive from a basic kinematic equation into something that we call the time of flight equation. Okay. Okay. So the time of flight equation is I don't know why this is not staying focused. This is arguably my most important video, and my camera will not lock in on what look at that. It's like all fuzzy. Okay. Why is it not? Do I need to have my hand here so I can like focus like kind of on my hand? Yeah, that's so weird. When my hand's there, it focuses. Okay, whatever. I'm gonna move on. Okay. Starting with kinematic equation, I'm going to start with a basic kinematic equation. So that's y equals y naught plus vy naught t minus 1/2 g t squared. Now, one thing that's important to note about this is that this equation, these derivations that I'm going to do, only work for ground-to-ground launches. So that's going to be where you've got maybe like, this is like the flat ground, and you've got a projectile that is launched and it lands at the same height that which it was launched from. Okay. Shoot, maybe there's like a gap between the two, but as long as it returns to the same height at the end, then it's all good. Okay. So that's what I'm going to use for this. I'm going to start out with this kinematic equation right here. Well, what I want you to recognize is that if I use this kinematic equation in a ground-to-ground launch, my initial height is the same as my final height. So if I subtract y naught on both sides, okay, this ends up being 0. Wait, those end up being 0, right? So you actually get 0 equals vy naught t minus 1/2 g t squared. Okay? And when you do that, okay, you also need to recognize that, especially for a launch like this, you're launching at an angle, okay? And it's typically, with respect to the horizontal. And you need to recognize that, that your y component of the velocity, okay, is going to be equal to your initial velocity, the net velocity, times the sine theta of that. Okay, so you're doing v naught sine theta to get the y component of your velocity. And when I make this substitution into here, I get 0 equals v naught sine theta t. Okay, and put that in parentheses so you can know it's separate from everything else. 1/2 g t squared. Now, what I can do from here is I can actually factor out my t's because I've got a t in every term here. And this will actually give me, I'm going to move this to the left side of the equal sign. Okay. This will actually give me t parentheses v naught sine theta minus 1/2 g t equals 0. Now, this right here, I'm totally blanking on what it is, on what we would call this. This is what we can say, right, to make this equality, to satisfy this equality, is that we can actually have t be equal to 0, and then the whole thing turns into 0, and that equality is satisfied. Or what we can do is we need to figure out whatever's inside the parentheses and set that equal to 0. So that's exactly what I'm going to do. I think t being equal to 0 is a given, okay? So this is true if t is equal to 0, but the projectile's got to fly for some time, right? It's got to fly for some amount of time. Otherwise, it's not flying at all. And then why are we even solving it, right? The time of flight is 0, okay? So I can actually just take what's inside my parentheses here, v naught sine theta minus 1 half gt equals 0. I can just take that and set it equal to 0. And then I need to get t by itself to see what satisfies this equality. I'm going to subtract v naught sine theta on both sides. Okay, 1 half gt equals negative v naught sine theta. And I can cancel out my negatives here, which is fine because I don't like to have the negativity. Okay, it's Valentine's Day. There shouldn't be any negativity. And then all I got to do is multiply by 2 and divide by g. And I end up getting the time of flight equation, which is just 2 v naught sine theta over g. Okay, and I think this equation we've done a more we've done a derivation of this extent, I think, in Physics 1, probably also Physics C. Um, and so this is probably not anything too. This is really just 2 times v sorry, two times vy naught over g, right? So that's kind of like the short form of it, but vy naught is equal to v naught sine theta. So you'd have to make that substitution anyways. This just has it all rolled into one step. I prefer having everything rolled into one step because then my life is a little bit easier, right? And when my life is easy, I'm happy. Okay, the next thing I'm going to do is I'm actually going to go completely separate from this. I will use this later, but I'm going to go completely separate and do the kinematic to trajectory equation derivation. Okay, what is the trajectory equation? It's a equation that basically defines the parabola that which the object travels through. Okay, and so it's not really like something that you would. It's more like something you would graph, and it shows you the trajectory of the parabola, right? Okay. So what I'm going to do is I'm actually going to start with my basic kinematic equation for x. X equals vx naught times t. Okay. And I am going to, and there's no acceleration in the x direction, so there shouldn't be any acceleration, and our initial position is going to be 0. Okay. Well, from this equation, I can get that time is equal to x over vx naught, and then I can show that time is equal to x over vx naught is just v naught cosine theta. Okay. Okay. So now what I'm going to do is I'm actually going to use this knowledge, and I'm actually going to plug it back into the equation that I started with. Now, the trajectory equation is not limited to being used by ground-to-ground launches. You can use it in non-ground-to-ground launches. So, for example, if you start at a certain, if you start like, up high or whatever, and then you end up landing down low, and this is what you do, the trajectory equation will actually work for this too. It doesn't have to be a ground-to-ground. Okay. So what I'm going to do is I'm going to write my position equation for the vertical position equation. Okay, y equals y naught plus vy naught t plus 1 half g t squared. So sorry, this should be a negative right here. Okay. Okay. Because your y direction always has negative direction, right? Or negative acceleration, right? Or the acceleration has negative direction, right? Okay. Technically, I was right every single time I said it, right? Okay. And then what I'm going to do is I'm going to make my substitutions in here. I'm going to substitute my t's. I'm also going to substitute my vy naught is equal to v naught sine theta. Okay. Okay, so I'm going to do y equals y naught plus, and then vy naught is going to be v naught sine theta. T is going to be x over v naught cosine theta. I know it's going to look like a mess. And then I'm subtracting. This is going to be 1 half g t squared. So this is going to be 1 half g, and then t squared is going to be x over v naught cosine theta squared. Okay. Okay. this y naught's just going to kind of chill. He's not really going to do anything. What I'm going to do now though is I'm actually going to condense this middle and this end term to all be inside of one fraction, so that or to all be in one fraction each, so that I can make it at least a little bit nicer, and I can actually cancel out some stuff when I do that. So when I add this, this is going to be x v naught sine theta over v naught cosine theta. Okay, minus, when I do this, this is going to be gx squared over 2 times v naught cosine theta squared. Okay. Okay. And all I got to do here is on this middle term right here, I got to recognize that my v naughts are going to cancel out, and then sine theta cosine theta, that's tangent theta. Okay. Did you catch that? It's tangent theta, okay? So this ends up becoming y equals y naught plus tangent theta x, okay, minus g over 2 v naught cosine theta squared times x squared. Do you recognize that this is quadratic? Okay, this is quadratic. Okay. Typically, you have a ax squared bx c, right? This is a quadratic equation. Okay, and it does give me a parabolic trajectory. Okay. Okay. That is the trajectory equation. Okay. Now I'm going to show you the final step here, which is where I'm going to go. What I'm going to do is I'm going to go take both of those equations that I derived. Okay, both of those equations, and I am going to now derive the range equation from there. So I'm going from the time of flight and trajectory to the range equation. Okay, so I'm going to combine both of those equations to get the range equation. Okay, I'm going to start with the trajectory equation, y equals y naught plus tangent theta x minus g over 2 v naught cosine theta squared, okay, times x squared. Okay, so there's my trajectory equation. Okay, so that's a g on the top there. My handwriting is very sloppy, if you haven't noticed already. Now, I have to remember that I'm looking at a ground-to-ground launch. The range equation only works for ground-to-ground launches, right? So if it's ground-to-ground, okay, so this is, again, like flat ground, ball goes and lands at the same height that which it was launched from. If it's ground-to-ground, that means that this right here, y and y naught, are both going to be 0, okay? They're both going to be 0. So this ends up being 0 equals tangent theta of x minus that. If I factor out the x's, okay, then this is going to look like tangent theta minus g over 2 v naught cosine theta squared times x, okay? And this is very similar to the time of flight equation. Actually, now that I think about it, I don't even think I'm actually going to use the time of flight equation in this. I think the time of flight equation is just helpful to get, okay? But I don't even need time in this equation. As you can see, I've already eliminated all my times, so it doesn't even matter. But what I'm going to do, okay, is I can say, yeah, x equals 0, and that'll turn this whole thing into 0, right? Or I can take what's inside the parentheses and set that equal to 0, which is what I actually want to do, okay? Because one of my solutions for this is going to be when x equals 0, but that doesn't really, I mean, then projectile hasn't been launched yet, right? X is the range, or the distance the projectile goes horizontally, right? So I'm just going to take what's inside the parentheses, tangent theta, okay, minus g over 2 v naught cosine theta squared times x, set that equal to 0, okay? And I need to get x by itself because that's going to give me my range. The first thing I'm going to do is subtract tangent on both sides, okay? g over 2 v naught cosine theta x, okay, equals negative tangent theta. And I'm actually just going to cancel out my negatives right there, okay, so that I don't have to worry about them for the remainder of the problem, okay. I don't like having the negatives there. It just makes things weird. I'm just going to take them out, okay. Okay, now I'm going to multiply both sides by 2 times v naught. Oh, sorry, this should be squared right here. By 2 v naught cosine theta squared. And that's going to give me, that gets rid of that on down here. So I get gx is equal to 2 times v naught cosine theta squared times tangent theta. Now, what I'm going to do here is I'm actually going to expand out this v naught cosine theta, okay? And that's going to give me gx equals 2 v naught squared times cosine squared theta times tangent theta. And if I remember from earlier that tangent of theta is simply equal to sine of theta over cosine of theta, okay, then all you got to do is, I'm going to replace that in there because that's actually going to help me cancel out a cosine, okay? It's going to help me cancel out some of my trig functions, right? The more trig functions I can cancel, the better off I'm going to be, right? Okay, so what I'm going to do is I'm just going to plug that in there. I get gx equals 2 v naught squared cosine squared theta over, oh sorry, times sine theta over cosine theta. And this looks really ugly, but bear with me because I'm almost I'm almost done here, right? Bear with me because I'm actually really close to the solution. I got to realize that my cosine down here and another one of the cosines on the top cancels out. Well, then you're going to notice that you're going to notice, hopefully, that I'm left with 2 times v naught squared times cosine theta times sine theta. If I actually pull out this 2 cosine theta sine theta, this is actually it's actually one of your identities from pre-cal, okay? This is the identity 2 cosine theta times sine theta equals sine of 2 theta, okay? So I'm going to now use that substitution because having all this stuff in there is so ugly. And you can keep it. You can keep it if you want. I don't want to keep it though. Okay, so I'm going to substitute that in there to get a new form, which is gx is equal to v naught squared times sine of 2 theta. Oh, sorry, there's nothing on the denominator yet. But I am going to divide by g on both sides. So that ends up being x equals v naught squared times sine of 2 theta over g. Okay? All right. That's the range equation. There it is. There's other ways that you can write this, if I'm not mistaken. I think because what you can do is if you recognize right here that v naught squared is really just v naught times v naught, then you end up getting a v naught cosine theta and a v naught sine theta, and that's just v sub x, v sub y, okay? I don't like that one as much because this has every step rolled into it. I really, oh, and then you have to multiply by 2, of course, but I really do prefer having every step rolled into it. So this equation is incredible because it has no time in it, so you don't need to know the time of flight to actually use the range equation. You just need to know the speed and the angle that it's launched at, and then obviously the value of g on whatever planet you're on, but there's a good chance you're launching a projectile on Earth if you're in like high school physics or maybe even college physics, okay? All right, well, this'll help you as, prom's nearing. This will help you for prom, right? Okay, well, that's my Valentine's Day special for some physics, okay? All right, well, I guess I'll catch you on the next time. Go boss it up.